Okay, everyone. Good afternoon. Thank you to each of every one of you for being here with us today, and we are pleased to welcome you to our competition, is Youth Idea Competition 2022. And of course, for our Youth Idea Competition contestant, thank you for able being here on your final exam sessions. Much appreciation for you, and also I welcome you from I'm welcoming for all of the contestants from Institut Teknologi Bandung, Institut Teknologi Kalimantan, Universitas Brawijaya, Universitas Gajah Mada, Politeknik Negeri Jakarta, dan Universitas Indonesia. Okay, Youth Idea Competition 2022 is a series of competition organized by the National Battery Research Institute. Then this competition is the third event after being successfully held in June 2022, and this event will be part of the International Conference on Battery, the International Conference for Advanced Materials and Technology. And NBRI YIC 2022 aims to be a forum for participants to share their idea and innovation at the international level. And I would like to invite our honorable judges. Our first judges from founder of National Battery Research Institute, Prof. Dr. Renat Evi Kartini. And the next person beside her is Professor Anne Zulfia, as Professor of Composite Material in the Department of Metallurgical and Materials Engineering. And to all contestants, you have 5 minutes for presentation and 5 minutes for questions and answers. And please bear in mind, we hope that all the contestants can compete in a healthy manner and try your level of confidence. And let us begin with the first presentation entitled Biomass Derived Carbon as an Environmentally Friendly Material for Supercapacitor Electrodes, delivered by Faraday team from Bandung Institute of Technology. From Faraday team, time is yours.
Okay. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, Your Honorable, to all of the judges and audience in the room. We are all welcome all of you to our presentation session, namely biomass derived carbon as an environmentally friendly material for supercapacitor electrodes. Okay. Before we deep dive into our research, please allow us to introduce ourselves. My name is Aziz, and these are my friends Rizky and Ade from Faraday team representing Bandung Institute of Technology.
Okay, next. Okay, first of all, I would like to explain about supercapacitor. So from that diagram, we know that supercapacitor can be used as energy storage with high power density. And supercapacitors consist of an electrolyte, electrodes, and membrane separator. Next. Okay, there's 3 types of supercapacitors: electric double layer capacitor, pseudo-capacitors, and hybrid. But the most commonly used is electric double layer capacitors with carbon-based electrode. Next.
Okay, so the root of the problem is 1,477 metric tons of waste produced in Bandung City, which 63% can be classified as organic waste. But unfortunately, 54.7% of the waste is being in a dump field. Okay. And the organic waste is a natural carbon source that have a high surface area, high porosity, and leading to good ion mobility and produce electrical conductivity. Next. Okay, so these two are the most known energy storage in the market. The first is lithium-ion battery, and the second is supercapacitor. So supercapacitor recently gaining huge research development due to its high power density. So we conduct research to produce carbonaceous materials from biomass, starting from impregnation stage, pyrolysis stage, and then produce carbon electrode, and then electrode performance analysis.
So here's the methodology that we use in this research. So we basically did the experiment and also did the literature studies where the experimental studies where the experiment was involved in steps as shown in the display. So first, we have to prepare the biomass agents, and then we have to prepare the potassium hydroxide solution. And next, we impregnate the biomass agent for with potassium hydroxide for 24 hours with the concentration of 5 molar to increase the surface area. And then next we kind of the watering the liquid that resulted from the previous step, and then the dried biomass was inserted into a muffle furnace to conduct the porosity of to conduct the pyrolysis process, and then we come the carbon fabricating, and then assembling the electrochemical cell, and then the end was we conduct the electrochemical performance testing for the carbon electrode. Next.
Okay, so next shows in the picture is micrograph for food waste carbon electrode. It shows a high porosity area after it goes through a pyrolysis at 700 degrees Celsius temperature. Okay, next. Okay, so here's our other micrograph pictures from sawdust carbon electrode. It also shows a high porosity after going through a pyrolysis at 800 degrees Celsius temperature. Okay, so it leads to a good ion mobility.
Okay, by using potentiostat, we get this cyclic voltammetry curve, and from this curve we determine the specific capacitance of electrodes from biomass. And from here, this is the literature review that there are some electrodes from various biomass that has variative specific capacitance value, and this value is depend on the certain condition such as temperature of pyrolysis and impregnation solution, etc. Next.
Okay, so from the presentation we can conclude, first, biomass derived carbon shows a promising properties. Second, biomass is an abundant and cheap material to be used as a supercapacitor carbon electrode. But from our research, we also have several backdraw. The first, low carbon yield. Second, high energy requirements. And third is long activation time. Okay. We would like to say thank you to all the lecturers from different laboratories in metallurgical department. And next. Okay. We would like to convey our deepest gratitude to National Battery Research Institute for this huge opportunity. We were so grateful to be here.
Okay, everyone, it's time for question and answer for 5 minutes.
Thank you for your presentation. Thank you. Lisa. Carbon from the biomass. Okay, thank you for your presentation. First of all, I would like to ask about the carbon that you made from the biomass. Yeah. So, how to measure the porosity as well as the surface area of this carbon? What the dimension of the carbon? Is it a nano size or micron size?
So the image shows the micrograph is in nano size.
Nano size. What the size?
Okay, so from the literature view, can we show the presentation? Okay. Bukan yang itu. Oh, yang sebelumnya? Yang setelahnya satu sekali. Yeah. So in this case, the sawdust. So the range of the porous size is the range from 500 nanometers to 15 micrometers.
From 5 nano to
Yes, 500 nanometers to 15 micrometers.
500 nano.
From the largest to the smallest.
So what's the method you measure? Do you use the BET?
I'm sorry?
Do you use the BET to measure the porosity as well as the surface area?
Okay. So we combine between the actual research to fabricate the carbon electrodes and also the literature studies that we shows in here. So because we have certain limitations to use the scanning electron microscope in our campus, so we cannot obtain the actual data from our carbon electrodes.
One more question.
Okay.
So your biomass here is actually from the wood, yeah, sawdust. So you
Okay. So
small size.
the sawdust is actually coming from the biohydrometallurgical lab. So it's actually from like a manufacturing, and we utilize it to be the carbon electrodes.
Yeah, first of all, you have to clean it by soda. Yeah, by soda.
Yes, it's already in a small piece.
Yeah, small piece, and then you clean it.
Pardon, I'm sorry.
After you have the sawdust, you
Yeah.
clean it by
Oh yeah, yes,
by
yes.
Helium hydroxide.
Yes, yes. Impregnation stage.
What's the molar of the helium hydroxide?
Oh, four molar.
4 molar. And how long?
For about 1 day.
1 day.
1 day.
So you soak in 1 day.
Yes.
So do you measure the carbon content in your material? Because I know that you have done this pyrolysis, yeah, but the composition of the carbon I think not pure, perhaps 85% or 95.
Okay, so the
purity
composition
of the carbon here, the
for-
purity of the carbon, because your carbon will be used for the capacitor, right?
Okay, so the compositions, we actually, in fabricating the carbon electrodes, we actually combine between our carbonaceous materials from the sawdust and the activated carbon that we have in our laboratories from the coconut shells. So the ratio is 4 carbonaceous materials and 1 is the activated carbon from coconut shells.
But I want to know the purity of the carbon actually. the purity of the carbon.
Oh, the purity. Oh, so yeah. We
Because
don't
you have 4 kinds of the source of the carbon, right? And then what's the best one between sawdust and then the coconut shell and others?
Okay. So we have limitations when we do the research. So we cannot conduct any characterization. It is optical or the composition like X-ray diffraction or the scanning electron microscope. So we obtain, so we like combine between our data from our research and also from the literature.
I guess if you do the SCM, you can link to the EDX in order to determine the element content in your research.
Yes. Okay, so thank you for all of the question. We were so grateful to be here. Thank you so much. Good afternoon. Wassalamualaikum warahmatullahi wabarakatuh.
For next presentation is followed by MYT Jaya from Institute Teknologi Kalimantan. Please present your idea in front of the stage. Thank you. Okay, the presentation is start from now.
All right, thank you very much. Good afternoon, judges and everybody here. We are from MYT Jaya, Institute Teknologi Kalimantan, and today we are going to presentate about green synthesis of zinc oxide nanomaterials using Tectona grandis leaf extract.
Okay, nanomaterial is the most popular N-type semiconductor metal oxide because it's non-toxic, biocompatible, and chemical stable, and application for the many fields, especially on dye-sensitized solar cell or DSSC development. The synthesis method we use the biological because it's simple and we can improve about improve the novelty that we use. And for next, okay, for M and benefit, for the first determine the structural characteristic of ZNO nanomaterial, and the second one used as photonada in the DSSC. This is for the novelty using Tectona grandis leaf extract as bioreductor with the zinc acetate dihydride as the precursor. This is the methodology. Tectona grandis leaf, we dry and ground be a powder. The powder we will heat and filter with the distilled water. The distilled water had the leaf extract and zinc acetate. We mix and stir, and we get the precipitate. The precipitate we wash again and dry until we get the brown paste. The brown paste we calcination until we get a ZNO powder.
Okay, and next result and discussion. For figure 1, it shows FTIR spectrum of Tectona grandis leaf extract. An OH bond in the leaf extract that acts as a reducing agent, and formation and stabilization of the nanomaterials was confirmed at peaks at 32 and 90 per centimeter. And figure 2 shows FTIR spectrum of the nanomaterials. The absence of absorption peaks at wave number between 4,000 to 1,000 per centimeter indicates that the resulting ZNO has high purity. Next, then figure 3 shows SRD profile of the ZNO nanomaterials. It shows the formation of pure hexagonal wurtzite structure zinc oxide with 4.48 plus minus 0.06 nanometer crystalline size. And next, from this presentation, we conclude that one, the synthesis of the nanomaterials has been successfully carried out using green synthesis method, and two, the presence of OH group in Tectona grandis leaf extract indicate the ability of the extract to produce the nanomaterials, and three, the synthesized the nanomaterials had pure crystallinity with hexagonal wurtzite structure and revealed crystal size of 4.48 nanometer. We would like to thank to the Department of Physics, Institut Teknologi Kalimantan, and then lecturer in Department of Physics, Institut Teknologi Kalimantan, Ms. Tutreni Septiana. And then we would like thanks to the Integrated Laboratory Institut Teknologi Kalimantan. Next, this part reference, and then thank you. Thanks for your attention.
It's time for question and answer. Start by now.
Okay, thank you. So you have what is your main goal? Your main goal to choose the Tectona grandis leaf. Why? Is it abundant in Kalimantan or what?
Thank you very much for the question. So why we choose Tectona grandis leaf? Because yes, is it very abundant in our place in Kalimantan, and we use it because it have more flavonoid than we already
What is in Indonesian? In Latin. What is Indonesian name? Tectona grandis.
Thick leaf, daun jati thick leaves.
yes, actually it's very abundant, and mostly Tectona grandis leaf never have any benefit, so we want to use it, especially in our place. It's very we want to use it for nanomaterials development.
So at that time you mentioned that you choose the biological synthesis methodology, yeah, or green synthesis. In comparison with the other methodology, what is the advantages of this?
So the difference is the conventional method, physics and chemically, is very expensive, and it's more hazard because it use more toxic materials, and it's more simple to get the Tectona grandis leaf.
Do you have waste during the preparation of this material? Waste during the preparation. Produce waste? What kind of waste?
Hanya sampah dari ampas.
Only from the leftovers of the Tectona grandis leaf.
But that waste it's
very safe.
Very safe, yeah?
Yes.
So, okay. Okay, can you go to the experiment? Can you show the experiment?
For the methodology.
I want to ask you that, well, you do finally the XRD, but to, as Professor Anna said that at the beginning, how do you know that is it's containing the zinc oxide there? Because that actually the best way to do the method is you have to see what is the material, the content of this material, yes, using ADF probably, yes. But you do directly, and then you found you found the zinc oxide there. And then when you do this, so there are several process, yes, and you mix with this the leaf extraction. What is the temperature when you do this? I mean calcination, and then how long the precipitation takes time?
Waktu kalsinasinya 500. Terus berapa For the calcination is 50,000 Celsius and 500 Celsius, and for the calcination for 19 hours.
19 hours.
Yes.
In which temperature?
500.
500
Yeah.
temperature. Okay. So did you do the EDS?
Yes.
You do the SEM, scanning the microstructure?
No, actually no. We just want to confirm with take
Yeah, but how do you know that your material in nano? How do you determine?
from the structure.
Structure
Which
crystal.
structure?
Structure crystalnya is size.
Crystallography. Can you go to crystallography result? Yes.
Crystallite size.
Okay, so you obtain the crystallite size. Yes.
Yes.
How do we determine the crystallite size from the peak, the bragg peak? Just brief. How do you get that? Which one of the peak that telling you the crystallite size? Which one? The width or the intensity or the position?
We actually use from reference in Retica and mod software, and we compare our data from the database.
From the database.
Yes.
So, but did you do the analysis, the XRD analysis using this your material by yourself?
Itu dengan database tadi.
Yes,
Okay.
from the database.
Okay. Yeah, actually, the crystallite size can be determined from the full width of maximum. Okay, from
Yes.
the width,
Yes.
right? Yes. So, yeah, it will be combined and then some break law, and then so you determine the crystallite size. Yeah? Okay, I think time is up.
Time is up.
Okay, thank you.
Thank you very much.
Okay, thank you very much for the attention.
Okay, for the next presentation from IHE team from Brawijaya University. To IHE team, the stage is yours. Okay, the presentation is start from now.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone, and honorable of the judges. And our team are Iwayan Wirayuda and me, Faisal Maulana, and Vita Valiana. We want to present our research idea with the title "The Influence of Concentration and Stirring Speed of Electrode Deposition Methods for Synthesis Manganese Dioxide Carbon Composite Supercapacitor from Polyethylene Plastic Waste." Electrical energy demand is increased for 10 years in Indonesia, and it means we need storage energy device like supercapacitor. But supercapacitor in electrodes still hard to gain, and we need another potential material to improve this one, like active carbon. I'm sorry, because this material is it a fine economical conductivity and high surface area. And then, I'm sorry. Yeah, why plastic waste? Because Indonesia, the second largest of contributor of plastic waste, and we need to reduce it. But carbon active need adding manganese dioxide for optimization, because active carbon has weakness like resistant properties and high energy consumption. And for next composite, for composite diaphragm, we using electron deposition method, and this method fabrication simple fabrication, short time to produce precipitate, and affordable high capacity. So for control precipitate amount of precipitate, I mean we need voltage or concentration of solvent. And then our aim is efficiency of manganese dioxide synthesis time, and have several advantages like one-step process, low cost, and simple process characteristic, and high capacity. So now our novelty is optimization of the conductive material from plastic as a supercapacitor electrode material by adding manganese dioxide with electron deposition method.
And now for the method is the first to activate carbon produced from the polyethylene plastic waste. It's the first for heat in removal furnace, and then after that immerse in acetone for 24 hours and then dry it. And for the carbon, activate carbon we're using to electron deposition method. And the second method is the electron deposition using the manganese sulfate and natrium sulfate as precursor with the various concentration 0.5 molar and 0.25 molars. And then after that, we get the result and stirring with 300 rpm and 600 rpm. And to prevent agglomeration, we using the ultrasonication. And then for the characterization, we use three characterization: topography measurement system, particle size analyzer, and capacitance. And for the topography measurement system, for now the surface area, and the alternative to know the pore size is the 0.35 molars has the 6 and 10 nanometers, and for the 0.5 molars has the 1 and 2 nanometers pore size, and the high surface area in the 0.5 molars and 300 rpm. And for the particle size analyzer, we can see in the 0.5 molars for 600 rpm has the height size it the 700 nanometer, and then for the 0.25 molars has in 600 rpm with the almost the 600 nanometers too. And then for the capacitance, as we can see in the data, for the manganese dioxide composites has a 0.6 ampere per meter quadrat and the highest value of 53 farad per gram, when the capacitor commercial just only about the 0.0035 ampere per meter quadrat. It's because the manganese dioxide distribution of the various concentration in 0.5 molars has the dominant distribution manganese dioxide, so it can store the charge when doing the store of supercapacitor and can to reduce the size of pores. So in the composition from our idea is the form of porosity manganese dioxide carbon, and the particle size become more uniform at low concentration and the high peak, and the storage has higher its capacity is equal to 53 farad per gram in the one sample 0.5 molars at 300 rpm. So for the advancement, we thanks to million autodidacticity, and we have to provide faculty to conducting the research. So this is our reference we using in our research. Maybe just for our team, maybe to return to moderator.
Okay, thank you for the presentation. Now we are going to the question and answer session. Start from now.
Okay, it's quite interesting title your papers here. So here you made the carbon from the
Plastic polyethylene.
plastic waste,
Yes.
PET, and decompose become.
Yes.
So how to decompose this PET?
Pardon me?
How to decompose the PET? Because in PET we have other elements such as protein, and others. Yeah. How to decompose?
Okay. Range of
Any chemical reaction?
okay. Maybe from physics, as we know, when we take it in methylphenance with thermal degradation in range 450 degrees Celsius for 2 hours, we can get the carbon, but it's still not activated. It's still just a carbon. Maybe for now more, we should now in FTER, but from our research, we can now in our research it get the black carbon, and after that to now deactivate it, we should to immerse in the acetone for 24 hours, so it can making the open the pores from the carbon, so it can show activated carbon. Maybe such as that.
Yeah, the activated carbon actually you want to make more active.
Yes, for make
For
to
porosity.
create a porosity from the carbon.
Porosity,
Yes.
So here you want to make the capacitor from the mangan dioxide and carbon become a composite materials. So I think I cannot find here in your I cannot find in your paper here about the XRD result or FTER of these materials. So I think it's better if you can put some result of FTER.
I actually want to this if we have more funding research, maybe we just using characterization in our university such as topography measurement system we have in our university and it's free, and for the particle size analyzer we have in our university, so we can using if we have without using the money.
So you use the stirrer, to
Yes.
combine these materials.
To combine and bind strongly the composite.
Yeah. So how long that you find for this material can mix homogeneous?
Okay.
Because we want to mix this homogeneous between mangan dioxide and carbon.
For the homogeneous with using the magnetic stirrer, we use for the time 1 hours, and after that to prevent the agglomeration, we using the sonication to prevent the agglomeration, because after we did the electrodeposition and still dead, sometimes it has to agglomeration. So to prevent this, we also did the ultrasonication for 1 hour steering with various steering speed, and after that we do the ultrasonication.
Because this disadvantages of nanosite is agglomerate, so you need to do more sonification in order to find the individual particles.
Yes, to get not more size from our particle.
Yeah, because agglomerates become large particles.
Yes.
So here which one is better? Is 300 or 600? 300 or 600?
Okay, for the capacitance, we get in 300 LPM in 0.5 molars because it has distribution mangan dioxide very dominant. But if we look from the particle size, it has a like in 600 LPM. So we think it's very good in and better in 300 LPM because not many the mangan dioxides close the pores, but it has the dominant distribution. Maybe this.
Okay, I think it's a good idea that you make the carbon from the PET waste here, because we have so many PET waste around us here, so we have to reduce this become a valuable materials here in order to have a carbon active from this waste. Okay, thank you. Good luck.
Thank you.
Okay, thank you, team IAG from UB. So let's moving on to Aruna team from University of Gajah Mada. To Aruna team, the stage is yours. Okay, the presentation is start from now.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. I would first like to thank to the committee to organizing this competition. My name is Hadi from the Aruna team. Today, I would like to present our research entitled Utilization of Rotten Carrots as a Source of Activated Carbon Prepared by Zinc Chloride Chemical Activation for Supercapacitor Electrode Applications. Next. Research on energy storage is one of the important topics today, as it becomes the solution of energy crisis. Some example is batteries and supercapacitor. So, what is a supercapacitor? Supercapacitor is a device that can combine electrochemical and electrostatic mechanism, resulting in higher power density than batteries and higher energy densities than capacitors. Activated carbon is the major choice of the electrode materials for supercapacitor, and it can be obtained from various biomass. And here we will use the rotten carrot as it usually weighs in large quantities without any benefit in our daily life. Next. So the goals of this research were synthesis of activated carbon from rotten carrots, and study the effect of activation time from 3 to 4 hours, and analyze the morphological features, structures, and electrochemical performance of rotten carrot derived AC. The novelty of this research is the rotten carrot derived AC is rarely found. The other researchers have studied the activation temperature, and therefore this research will study the activation time. Next. Our main material is clean dry rotten carrots. The first step is carbonization, and there was nitric acid to remove the impurity. After that, we carbonize carrot at 600 degrees, and then we mash and sieve the carbon to be the carbon powder. And then the second step is activation by zinc chloride chemical activation and physical activation with 700 furnancing or calcination in nitrogen atmosphere. And then the result is washed by hydrochloric acid and then drying to get the AC powder. Next. As for the characterization, we use SIM-ADX to study the morphological features, as well as PSA to analyze the pore structures. CV and GCD were also conducted to finally evaluate the electrochemical performance. Next. Here is the result for SEM. The image showed the degradation of the particle size as the activation time increased inversely proportional with the dominant pore diameter. AC with a longer activation time broke the surface particle, covered the pore, the preformed pore, and then result a smaller pore size. This result assumes that samples activated over 3 hours will have a smaller pore distribution. Next. The next one is result from EDX. Elemental composition of carbon, oxygen, and zinc are listed in the table. As seen in the figure, the carbon represented by red dots is increased sequentially by the activating time. Thus, affect the carbon percentage inversely proportional with the impurity and vice versa. Whereas the zinc as a result from activation again is not degraded sequentially, in which signifies that the activation times doesn't reduce the again quantity. Next. This slides present the pore structure from PSA. It can be found that AC3 have weaker volume absorbed than AC4, resulting in lower surface area and pore volume. It could happen due to the long long activation time that ruins the pore structure. However, it does not affect the pore diameter of around 1.2 nanometer. The inspects pore size distribution prove the presence of micropores and mesopores. These pores are suitable for supercapacitors since the efficiency of charge storage mechanism and ion transfer. Next. The last one is the result from CV and GCD. The electrochemical performance is measured by a standard 3-electrode system in aqueous electrolyte. As seen in the CV curves, the highest peak occur at 3 IC3, confirming that the activation time higher than 3 hours affect the electrode stability and decrease the capacitance. And then regardless, all samples can exhibit power density higher than 500 watt per kilogram with the highest energy density of 1.23 watt hour per kilogram of AC3. Conclusion, finally from this research, we can conclude that rotten keros is successfully made and activation time higher than 3 hours affect the particle size and power distribution, in which the best electrochemical performance was achieved by AC3. Okay, that's all for me. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Okay, thank you for the presentation. And now we moving on to question and answers. Start from now.
Okay, thank you, Fatur. Okay, so my first question: why did you choose rotten carrot?
Because the first consideration is the rotten carrot is rarely found research in the Google Scholar or everywhere. I'm only find to journal, and it has a wide potential to be activated carbon.
Okay. But it's, that rotten carrot, it's also we eat that. Okay, so you compete with.
No, rotten carrot is the waste of carrot. We
Yeah,
can
but how do you find that?
Because
it's very the supply. Say I want to make the factory of the activated carbon from rotten carrot. How do you support? You are as a supplier of this rotten carrot.
This is research is my.
The quantity.
This is my research. Just only need a few samples, and I only take it from the garbage and the market in my place.
Okay. So,
but
yes, but of course, good in novelty is good. Yes, but sometimes we have to think whether it is possible to be scaled up, whether you can get that, if there is a factory want to produce this, how you have that? Yes, it's not so easy. Yeah.
Yes.
Okay. Can you go to the methodology? Can you move that one? Okay. So you did the experiment with the parameter of time, right?
Yes, activation time.
Time. Okay. So you use that 3 hours. So in where you make this 3 hours for in the furnace, the calcination, and then the other the same. So you go from crushing 1 hour furnace. Sieving, and then where is the 4 hour is here?
I'm just doing in this activation at furnace with nitrogen atmosphere.
Okay.
Only.
But the rest the same.
Same.
Okay. So you have the rest the same. So why did you choose that 3 to 4 hours, and then why it should be 700? So what happened if I make it 10 hours? And I increase the temperature to 1000 centigrade.
If, because my first conversation before this research exists, I just only use the other literatures that usually use 3 to 4 hours is many literatures. But if you use 10 hours, it's maybe get the worst. AC, because from my result that AC higher than 3 hours is get broke break the particle and cover the pore volume.
Okay. So how about the temperature? The temperature when we increase, what happened?
Temperature?
For example, 900. The calcination, the for activated carbon.
Oh, I'm sorry.
Why did you choose 700 instead of?
I choose 700 because the before journalists get the optimum.
Okay, so you based on the reference, yes?
Yes.
Okay. Okay. So at the end you have the target, yes, and then you do some characterization. Can we go on further to the characterization, right? Okay. So you do this three. Actually, did you do the XRD?
No, I don't do that.
Why?
Because in my goals or on my research is just get the high capacitance, and if XRD we use it to determine the structure, and it's not yet necessary for my research.
Okay. So you get the SEM. Can we see the SEM result? Okay. Yes, that one. Okay. So can you explain which one is the best, and then which part that is your carbon here?
From the CV measurement, the best is AC3.
Why?
Because we can look the particle is not yet broken, and it has still bigger pore size. But in this for AC4 this the particle has broken, and we can look the pore is can we see or and cover or enclosed by the particle broken.
Okay, so and the other the pore is more important, yes, most also important.
Yes.
Yes. So you measure the pore.
Pore.
Which one of the result of the pore?
Next.
Yeah.
Next. This result, actually the pore is inversely proportional with the result of the SEM, but I can use this data with strongly because this only use 2 samples because my the PSA device in my university is broken.
Okay. So my last question. So did you get the how you compare your result with the one already published, the previous result? Your data is good, comparable, or it's even better?
My data in surface area is lower, very lower than other literatures, but in the CV we get the specific capacitance that can in standard of the literature.
Thank you.
Thank you very much. Assalamualaikum.
Thank you.
Warahmatullahi wabarakatuh.
Thank you for the presentation. The next team will be Cemeng from Universitas Gajah Mada. To Cemeng, the stage is yours.
Check.
Okay, the presentation is start by now.
Okay, Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, the honorable all of judges. We are from Cemeng team. I'm the research supervisor Indra Perdana STMT PhD from Gajah Mada University. In this section, we would like to present our research. The title is Determination of Design Parameter and Optimization of Operating Leaching Process, Lithium, Nickel, Manganese, Cobalt from crossing NMC type ion batteries using sulfuric acid. So, along with the development of technology, the demand of battery, we can see in this graph, is increasing. And in the future, we have a new big problem about that, such as lithium battery waste. It has so dangerous to our environment because this waste is categorized into toxic and hazardous waste. So that is the background of our research to conduct recycling lithium battery waste into industrialization process, into sustainable process. So this research is to study the effect of operating condition and optimization of leaching process, and also determination of design parameter. The result of this process can be industrialization process to overcome the negative impact of lithium battery waste, so we can create a sustainable production.
And the novelty of our research is the raw material, which is the product of NMC battery waste crushing. So the main components of the raw material is consist of not only the cathode active materials, but also the anode active materials. And the research used the NMC type lithium ion battery waste from VR, sulfuric acid and hydrogen peroxide as leaching solution, and nitric acid and demineralized water as component analysis. And then we use a 3-neck flash to sequence as in the slide. And then for the research procedure, first the raw material is pre-treated to remove the unnecessary battery components, and then it will produce a powder of mixture of anode and cathode active materials, and then or can be called black mass. And then the black mass is analyzed, and then we go to leaching process. The leaching process is carried out in various temperature and will be sampled in minute 1, 2, 5, 10, and 20.
So that is the table of the raw material analysis of an MC lithium battery waste from VR. Based on this table, we can conclude that our waste is categorized in type 442. And then this is the effect of temperature process on person recovery. We can see in this graphic. Based on this graphic, the correlation of temperature between person recovery is positive, except in 7 degrees Celsius. Why? Because in this phenomenon, we get a decomposition process in hydrogen peroxide. So we can conclude that our research, the optimum temperature is 60 degrees Celsius. The effect of time leaching is the longer time leaching, we can get the higher percent recovery. We can see in this graphic, and we get the constant value. It means that our research is equilibrium has been reached. Based on this data, the equilibrium time is 20 minutes.
And after doing simulation for the data experiment, we get this graph. From the graph, we get the SSC result is quite small, so we can conclude that our mathematical model can be used to represent the leaching kinetics. And then the design parameter from the simulation we get is in this table, and the diffusivity of its component is increases with increasing temperature, except in the 70 degrees Celsius of nickel and cobalt. This phenomenon also occur in reaction rate constant parameter. This deviation can be happen at 70 degrees Celsius because of the hydrogen peroxide has the hydrogen peroxide is decomposed.
So the conclusion of our research first that the effect of temperature and time is have a positive correlation on person recovery, and we get the equilibrium time on leaching process is 20 minutes and the optimum temperature is 60 degrees Celsius, and the design parameter at optimum leaching the result is following. So that's all our presentation. The time will back to moderator. Thank you.
Okay, thank you for the presentations. Now we have to move on question and answer. Start by now.
Thank you, moderator. So I think it's quite interesting topic here. So you have nickel, mangan, cobalt, then you recycle the battery used and you recycle. Where can you find the battery used?
Okay, the raw material we using NMC battery lithium ion waste from VR. That is like
VR is like producing electric vehicle, like electric motor. So we get the material from VR.
VR.
Yeah, VR.
All right. So so you have this waste lithium ion battery, NMC cathode, yeah, then you recycle by hydrometallurgy process. Yeah. So what is the advantages of this hydrometallurgy process compared to the pyrometallurgy?
Yeah. Okay, the advantages of hydrometallurgy is a lower cost if we compare with pyrometallurgy, because pyrometallurgy method is using higher temperature between 1000 degrees Celsius until 2000 degrees Celsius. So if we compare in cost, hydrometallurgy is lower than pyrometallurgy. And the second is because the reason of environmentally, the hydrometallurgy is a more environment if we compare with pyrometallurgy, because pyrometallurgy produce like carbon dioxide and it's can pollute in air.
Yeah, that's right. So what do you think about this recycles method? Suppose that in 2030 we have electrical vehicles in our country. So of course this battery can withstand for I think five years or 10 years. So what do you think about this method in order to recycle of this battery use? Can we upgrade to the industry grade, because this is actually the laboratory grade? Yeah. What do you think?
Yeah, actually we can upgrade or scale up this research into industrialization process, because we know that President Joko Widodo have a promise to Indonesia. We go to electric vehicle, and the one NMC battery is so potential to for electric vehicle. Why? Because NMC battery first have a high density energy, and cycle process is the time cycle process is longer than the other batteries, and yeah, and after the why is that like maybe after the battery is into waste, we can using this parameter. It means this parameter actually can be utilized in industry. This parameter like diffusivity and constant rate to make reactor. So the core in this research is basically this constant rate.
And also the method that we use to pre-treatment the raw material is we use here is crushing. So if we have a large amount of lithium-ion battery waste in the future, we can also use this research because our pre-treatment method is crushing.
Okay, I want to ask one more question. In your table, you NMC.
Uh, Thank okay. Thank you for the question. So as I said before, the method that we use to pre-treatment the raw material is crushing. So we put all the components of the batteries into the crusher. So there will be all the components of the batteries like plastic, iron, copper, aluminum in the composition. So in the pre-treatment process, there will be slightly trace amount of iron in the black mass because the iron, right?
Iron.
Iron.
Ion, yeah.
Yes.
Oh.
Because the iron is the component of the batteries. It's like the shell for the batteries. So in crushing method, we put all the components batteries. So after the pretreatment, there will be slightly an iron component in the composition.
Iron come to your materials, but as you mentioned, that come from the switch.
The shell,
The
right?
Yeah,
Yeah.
the battery shell is
The battery
is
cell.
made of stainless steel, which is iron.
From the pack,
Yeah.
from the module, something like that.
Pardon?
Thank you. Good luck.
Okay, that's all our presentation. We say thank you to all judges to give me question and suggestion. Okay, thank you.
Okay, thank you for your presentation. For our next presenter is from PNG, Politeknik Negeri Jakarta. To PNG team, stage is yours.
Isinya udah berubah ya?
Okay, your presentation start by now.
Ya, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Good afternoon, judges. My name is Adil Asfa Proyegi. I'm as a team leader, and this is my partner, Tania Ininin. And this afternoon, by God bless, we can present to you our research about the effect of different electrolyte concentration and electric current on electrochemical synthesis of graphene using a solenoid modified reactor. Our background of this research is advanced material, especially graphene, that have useful. Graphene is very useful. We know that the graphene is very useful and be a game changer in the advanced material and in the development. Graphene can be photoelectrode in the DSLC solar cell, and it can be increase the effectiveness of the solar cell. And graphene can be raw material for battery and supercapacitor to grow up renewable energy and can be used to develop net zero emission from sustainable development goals.
All right, there are many research that have been done to find out or to increase the processing of graphene. So in this team, we want to find out what concentration and current is the most effective to produce graphene by using graphite exfoliation using a solenoid modified reactor. With the gain that we can get is increasing the effectiveness of graphene production using the graphite exfoliation process. From the previous research conducted by Isnanda Nuriskasari in 2022, their research is focused on variation of the anode and material and the solenoid reactor. So now in our research, we are focused on developed by comparing the concentration and the current. And next, our research is using electrochemical method. Why? Because this is cheap, fast, and the most effective to produce graphene in a large quantities. So this is the flow of our research. The first is we start from study of literature, continues to prepare our tool and materials, then building reactor, and next graphene production. We start from the first sample we try in 3 ampere, and the next sample is in 5 ampere. And each of the sample we variate in concentration 0.5 molar, 1 molar, and 1.5 molar. And then we find a result and discussion. From this graphic, we can see the effect of concentration of the graphene weight in current 3 ampere. And this graphite, we can see the effect of concentration at the graphene weight current at 5 ampere. So this figure show the process of synthesis. This picture is at 3 ampere with concentration 0.5 molar. This picture take an interval time at 10 minutes. And we do this process repeatedly for each sample. And in here, we can see the comparison of the effect of the concentration with current 3 ampere and 5 ampere on the weight of graphene. So this picture show the graphite after being synthesized that that we give the sample. It shows. And from all this graphene and picture, we make a result that the use of 5 ampere current for each electrolyte concentration variant produce more graphene than the use 3 ampere current. And then, based on the graph, it is found that the effective combination of the electrolyte concentration and the electric current is the concentration of 1.5 molar and 5 ampere. And next, from all our research, we find a conclusion that the greater the concentration of the stearic acid solution used, the greater the current flowing to the electrodes, the graphene synthesis portion will be increased so that the graphite is further erode and produces more graphene.
And this is, we would like to thank State Polytechnic of Jakarta and related parties who have helped and facilitate the entire process of carrying out this research. And next, and this is reference on our paper. That's all. Thank you for your attention. Thank you.
Okay, thank you for your presentation. The next is question and answer. And start by now.
Okay, interesting. So you have this, you made it?
Yes.
You produced?
Yes.
Right. So
from our result.
From your result, yes. So it means that it can be applied. So you have this, and also you design the instrument for the method.
For the reactors, yes, we designed that.
You design?
Yes, but we designed that by the previous research.
From the previous literature, yes.
Yes.
So you have that, yeah.
Yeah.
So how do you compare your result with the previous one? It's better or?
From the other method or?
Yes, yeah.
From the other method, we use the other journal that compare this method to the other method that concludes that the morphology is better in this method.
Okay. So normally we in processing or synthesizing graphene, they also made either bottom up or top down. Yes. So in terms of yours, it's mean top down. Top down it means that starting from graphite and then you make it graphene, and then but you can make also from the biomass or so you so you develop. So which one are you?
We make it from graphite, then to graphene.
Okay, so it means top down.
Yes, top down.
Okay. So what is a graphene actually? Why it should be graphene? What's the definition of graphene?
Why we use graphite?
No, what is a graphene?
Oh, graphene. Oh, graphene is a material or a raw material that we need to make a few. It's an advanced materials that we use to make a battery, a photoelectron, and supercapacitor.
Okay. So what is the most valuable of the graphene? So you can apply it, or either battery, supercapacitor, or other. What is the property of graphene?
The mechanical, the electrical, and the chemical. I think the graphene is very good, amazingly very good. That it can be a photoelectrode in the DSSC solar cell and can be raw material for battery and supercapacitor.
The other is it a part of the pore carbon or not? The graphene. How about the porosity? The pore of the graphene. You have that?
We haven't researched that. We haven't researched that yet now because we focused in the the current in the electrical and the concentration of the electrolytes.
Okay. Can you go to your go to experiment? Yes. Okay. Okay. So you have that. So you have that equipment, yes?
Yes, we have.
Okay. So how it works? How you develop that? Because you said that you develop it. Are you from which department are you?
I'm mechanical engineering, conventional energy.
Oh, conversion energy. So you develop also the equipment, yeah?
Yeah.
So how do you develop that one?
This is power supply that conduct electricity to graphite. This graphite. Yeah, this is the graphite. We conduct the electricity from this power supply, and this is accumulator for conduct electricity in solenoids to warm up, to heat up the electrolyte to be faster production of graphene.
Okay. So how long does it take to produce this one? The time. So you say that 3 ampere?
It's all, not just one run, is all of the run we produce that.
So for this research, we make the time is the one variable.
Okay.
In 1 hour. So to make in a bottle of that is not only if we make it in an hour, it isn't enough to make one bottle.
Okay.
We
So
just
several times. So in one production,
Yes.
1 hour, how
So-
many gram?
So
2.37 gram.
Okay. About
Is the higher.
Okay. So you have to do the to repeat, yes, several times.
Yes.
Yeah.
Oh, okay. Good. I think the last so the other applications, so many applications, yes.
Yes.
I think so you do also the SEM microstructure for this?
Not yet.
Oh, not yet. Yes, it's good if you do
We just,
the other microstructure. So you see that whether it's already in nanoscale or not. Yes.
We take it for another journal that the morphology, graphene morphology for from this method is better than other method.
Okay, thank you. Yeah.
Okay, thank you for the judges and for everyone.
Okay, thank you for the NG team. Now, last but not least, the presentation from Universitas Indonesia. The team name is Dear Future. To Dear Future, the stage is yours.
Can we? Okay, good afternoon, ladies and gentlemen. It's such a pleasure to be in front of you and present our idea. Let me introduce myself. My name is Atan Hasimbo, and here we accompanied by my colleagues. Here is Stella Yulia Andoko, and here is Ilham Arya Satya. We will present our idea related to advanced material for sustainable development goals toward net zero emission, entitled this potential application of carbon quantum dot synthesis from rice host waste composite as advanced solar cells to increase photon energy absorptions in maximizing solar panels power output productions. Next. Okay. Why do we need to do this? We all know that Indonesia has faced increase in national energy consumption, and the level and the number of the energy consumption affect much on our national development. And to answer this challenge, one of the answer is to maximize and optimize the renewable energy transition and renewable energy sources. One of this is solar panel. Why we use solar panel and why we choose solar panel? Because of its high known and its popularity, because of its high potential and its benefit could be comparing by the other renewable energy sources, made the solar panel has a lot of potential. But there is still more room to develop the solar panel. One of this is by optimizing the work of energy absorption to maximize the power output production. So that we need advanced material to maximize the power output production and energy absorption. But the material we need not just more powerful. The material we need it's also need to be environmentally friendly. So that we need some waste management to make an advanced material. Next, because of that, why we come up with the idea of using rice host waste, which has not so much use if we just leave it as waste, to be a way to accelerate our national energy transition and our sustainable development in energy sector. And here, the research goal are what we want to aim, what we want to achieve in our paper is that we wanted to know how to make the carbon quantum dots or CKD, and whether this method could be applied for the rice host waste or not. And then we want to know the energy analysis of the photon energy absorptions, and then the power output production of its material of the CKD based solar cells from rice host waste, and the cooperation of the silicon based solar cells. And because of that, we will do some research that conduct by this. Next. So the research or the paper that we wrote is a causal comparative method using the literature review, where the variable that we define here is the independent variable is the type of solar cells. The first is CKD-based solar cells from rice host waste, and the second is the silicon-based solar cells. And then it will affect and we will get to know the energy absorption, the photon energy absorption as the dependent variable. To get that results, we'll limit our research it just for the same type of solar panel, and then we just limit the research on literature review due to some time restriction and other technical issues, so we cannot make the real material that we want to sell to you. And what do we get from this kind of stuff, Stella?
Well, the big idea of our research is the implementation of CQD as a substitute materials for solar panels. Well, why CQD? What is CQD? CQD are a class of carbon nanoparticles with great properties, and which of many will be used in this research. The properties we will be using is its great properties in resistance and its great photon absorption ability. Why CQD? CQD has tunable properties. We found that CQD made from rice husks has much higher density than silica, and functionalized CQD enables us to enhance the property further. To make CQD, the first thing to do, rice husk trace will be going through a pretreatment process to ease carbonization during hydrothermal process, and then the pretreated rice husks will be rinsed to eliminate residues and any inorganic impurities, and then it will be synthesized using amino and carboxyl as functionalization agents during hydrothermal process. Well, what is hydrothermal process? Well, hydrothermal process is a process of carbonization and dehydration of carbon core in a specific temperature. Why specific temperature? Because temperature plays a big role on giving effect of particle size of the CQD. And next, the synthesized materials will then be purified using DI water, stands for deionized water, in Fisking tubing. And then this functionized CQD were characterized. And then the rice husk CQD will then be implemented into solar cells in solar panels, which has 5 layers, as you can see in the PPT. It has FTO, titanium oxide, and then CQDs, and then electrolyte and PT electrodes.
This is the energy analyzed between CKD concentration. The result is CKD can store and absorb energy with an PC, or power consumption efficiency, for 19.17%. That means the sunlight that hits the surface of the solar panel will be turned into usable electricity under the right conditions. This is the comparison analysis between rice husk waste and silicon. The photon energy observation of rice husk have 19.17%, and the power output projection produce 1.0 volts. On the silicon, the efficiency power is 10%, and power output projection is half volts.
Okay, so the conclusion that we get is that rice husk waste could be transformed and processed into CKD, and it has a high potential to applicate into the solar cell, to advanced solar cells. And next, we do consider that we have a limitation and shortcoming in the researchers, but considering the potential benefit and further development, we get and give the recommendation for these parties. Next, because we believe that advanced feature need advanced materials, and the advanced materials we need not just, as we said before, not just powerful, but we need the material that is sustainably environmentally sustainable. And because of that, that's our presentation. Roses are red, violets are blue. That's all we want to say, and thank you.
Thank you so much, such a wonderful presentation. Now we're moving on to question and answer. Start by now.
Thank you. So this is the last team. So you present your paper here is review paper, right?
Yeah, sure.
So you have read a lot of paper and you conclude in this paper.
Yeah.
So what's the difference between the
Okay, the comparison or the difference that we get to know first is that the compactness of the carbon rice and the CKD, the carbon column dots has a lot more compactness than that material. And then the second is that we get the CKD has the characteristic of superconductor more than that material, so that it could be more potential if applied as advanced solar cells. Maybe that's the simplified that we get.
right? You have done some research here.
Sure.
This kind of raw materials, right?
Yes. Yeah.
So
Oh, okay. So this name before that, I want to clarify this. This is not the exact material that we want to show. It's just a visualization using simplified material that we found in our course, and then we cannot provide the real material because of first is the time limitation. We don't have such enough time, and then the technical issue that we just get to know that we passed the full paper submission, and then yesterday we need to present the paper now. So, and second, we have a limitation in the finding, so we can use and we can make the process that we have known and to make the real material of the CKD from rice husk waste.
Yes.
So you carbon powder, right?
Yeah.
Is it from rice husk? You carbonize the rice husk.
It is
and you get-
visualized to be so. Okay. If our rice husk were to be processed, if we have the right tools, it will look like that. But in this case, we are limited on tools and fundings and time, so that is only a bit of visualization of what it would look like
But
if we
it's
were
not
to actually
from rice
produce
husk
it.
waste.
So it's not really from the rice husk.
Yeah,
Yes, it's
sure.
not.
I thought that this is the sequence. Of your
Sadly,
work.
it is
We,
not.
we also, yeah.
Large particles.
Yeah.
Yes.
Because in your presentation, you said that a CQD is nano level.
Nanoparticles, yes.
Okay, so why we get and give the visualization of this material, because we want to get to know that the CKD could be compact more into something more more clear, and we can see it by without microscope, and we can see it just with our naked eyes. So that we bring some material that have a similar characteristic when the CKD, the liquid composite of CKD, been composite and been compacted more, so that the results that we found in the paper, it found that it has similar characteristic with these rocks. Thank you.
The application of your CQD here for the solar cell panel.
Yeah.
So the efficiency is 19 point something.
Yes.
It is quite high. The
Yeah.
efficiency here.
Yes.
So because of this CQD.
We compare it and we analyze it, and we have conclusion that it's because of the CKD, because of the silicon, the efficiency of the silicon-based solar cells is lower than this, but we cannot provide, and because of there is a lot of solar cells, silicon solar cells out there, we cannot provide a simplified of efficiency of the silicon solar cells, but we do consider that it has higher efficiency, and this efficiency because caused by the CKD materials.
And if I were to add, it's because, as mentioned before, CQD has a property of higher photon absorption ability, and that explains why they have higher efficiency by around 9% compared to silicon-based, because of that property, also because it is much denser than normal silica. Yeah, and that's exactly why.
Alright. So if you want to make this layer in solar, layer is solar panel. So what's the materials you combine with the CQD?
Oh, we haven't provided some thorough analysis for that. What material that we better or the best combination for the CKD to apply in solar cells, but it will be interesting if we do some further research to find the combination of CKD if we want to apply it in a solar panel.
Mm-hmm. Because actually, perhaps you need the chemical solution, yeah,
sure,
in order to make slurry in the
sure,
your thin film of this top of the layer.
Oh, however, I do have something to show you about the chemical mixed into that. So if you can see in this process, in the synthesizing process, the CQD were made using amino and carboxyl functionalization. This is from past research, and we found that carboxyl functionalization agents resulting in CCQD, called CCQD, it has much higher particles, as you can see right here. This is the CCQD, and this is the NCQD. However, we still do not have the sufficient research for that answer yet, but we have these variations of amino and carboxyl functionalization agents for CQD.
Amino and carboxyl.
Yes.
Okay, so this research is still running, or?
We do hope that it could be continued and sustained, and we could make the real material and apply it in the solar panel. But yeah, we still need time for do that.
Okay. Thank you.
Thank you very much.
Thank you very much.
Okay, thank you to all contestants for delivering your presentation. That's all wonderful, totally wonderful presentation from you guys. And now we come to break session.